attachment, you know, the
Yeah,
poster. Okay, then.
Yeah, they are, challenges. Even though we tried hard yesterday,
Yeah,
that
right.
we shouldn't have any kind of connectivity challenges. But anyway,
Thank you.
that's
Thank you
we
for
need to.
inviting me, and thanks for your time, and sorry for being through this hassle of getting connected. Anyway.
So the way I'll do is I'll shortly introduce about the two organizations like UISMS and ECSF's partnership in this program, and I'll introduce you, and then you may, in the meantime, you can share your screen.
Excellent.
All right. So, right. So I think we should begin. You are able to share your screen.
Yeah.
Okay. So good afternoon or good morning or good evening, depending on where you are. So on behalf of ECO Science Foundation and the Union of Iranian Societies of Mathematical Sciences, UISMS, I'm delighted to welcome you all to our third lecture on the series of populating maths and science. My name is Khalil Raja, and I work as a program manager for the ECO Science Foundation. A very short introduction or background of the ECO Science Foundation, which is an intergovernmental agency of 10-member countries, including Afghanistan, Azerbaijan, Iran, Kazakhstan, Kyrgyz Republic, Pakistan, Tajikistan, Turkey, Turkmenistan, and Uzbekistan. So any of any participants do you have any questions, you can put it in the chat box, and we'll take them at the end of this session during the Q&A. And also, I would request that please keep your microphone off all the time. So we are fortunate today to have Professor Siamak Noorbaloochi, our esteemed speaker for today's webinar. And he was an assistant professor at Shahid Jamran University, Ahvaz, Iran, and a professor of statistics at Shahid Beheshti University, Tehran. He's currently a professor of statistics at Medical School, University of Minnesota, and statistician and investigator with Center of Care, Delivery, and Outcome Research. So he'll be presenting his talk on the Bayesian irrelevance of sampling design. Thank you very much for joining us again, and over to you, Professor Noorbaloochi.
Thank you for the introduction. And really sorry for going through this hassle. Yesterday, we had a good time getting connected. But what I want to talk about is something that I'm not a survey statistician, but I had interest in foundations of statistics, and I did some work on this Bayesian reformulation of sampling designs. So I just got the opportunity to talk about some general opinions I have about the sampling designs and how to get them within the Bayesian theory. It's very well known. This is a kind of general talk, and I wanted to put it forward that it has been since 70s, 60s even, that people talked about how Bayesian framework for statistical analysis does not conform with classical randomized Bayesian design, actually the design that are non-informative. Probability of selecting samples are independent of the observed outcome that we are trying to make inferences about. But the real thing is that why we are talking about it, because I have been in different meetings and talks, especially in meetings in Iran, younger generation, when they look at the older guy like me and they say, and I talk about sampling design, sufficiency, likelihood principle, stuff like that, they say, oh God, this guy is old. And the topics are kind of old. It's not of interest to the younger generation. But I am in two different worlds. And as an applied statistician, applying different designs on the real world, collecting data on health of patients and stuff. And as a statistical professor teaching different courses, there are a lot of different courses because of the need and possibilities. I noticed that we have to kind of introduce these old techniques that are so common all over the world to the new generation more. Especially, you know that sampling, the idea of randomized sampling, randomization, was really advocated by and propagated by Neyman. And then a lot of people, it became actually an official announcement by ASA that people have to use randomization in a suggestion, to use randomization in collecting samples, like the new announcement that ASA made against using p-values like 2-3 years ago. So I just want to talk a little bit about the importance of this and trying to kind of sell that still the story of randomization and sampling is very alive and influential, even in modern stuff. And then I will move to description of this relevancy of fixed sample non-informative designs with Bayesian analysis, which is very big in terms of it means designs are irrelevant. You don't need to do any sampling design, change your design stratification or do a stage, whatever design, successive design. Just you don't need to do any of those. The data collected is the end of the story. And I want to show that at the end toward this talk, I will present an idea that we had way back then in 2010 about coming up with a new Bayesian formulation of the sampling so that within that Bayesian formulation, design becomes relevant. That's more technical toward the end of the talk, but I will try to just start talking about what is very important rather than those formulas and garbages toward the end of the talk. First of all, just to remind everybody that one of the hottest topics in the statistical inference is causal inference these days, which started really by students of Cochrane, Rubin, and then different people, Robbins and his student at Harvard, and so many other people nowadays talk about this causal inference, and it has become a big story. If you want to publish a paper, really, you have to come up with some story about propensity analysis, and then maybe inverse probability weighting, and cloning, and creating some sort of causal estimates of causal effects. Okay. All of this story of propensity analysis and causal inference, which is very hot, is based on the idea of trying to approximate random assignment of treatments to patients. You see, randomization. The whole idea of propensity analysis is to create stratas given the propensity score, where within the stratas, the subjects are approximately randomized. And still within the at least I know, medical community, where new drugs are being invented, new procedures are being tried. I mean, a lot of clinical trials are popular. Randomization is a big deal. However, because of missingness and voluntary participation of the subjects, usually randomization are violated, total random assignments. And that's why different propensity analysis and trying to reduce bias becomes very essential. So one big domain is the causal inference, that randomization matters. The other domain is the famous random forest in machine learning. In machine learning, random forest and variations of random forest, in order to find importances of the variables, predictors, they have to permute the variables. So permutation, they permute a covariate against the outcome and regenerate the model based on that permutations and repeat that over and over. They get some measure of importance. Or the whole idea of random forest is just to create random regression trees and then somehow combine the ideas. And that assures them the estimates are unbiased. You know, I use this word unbiased intentionally because the whole idea of classical, and I just want to give you my own impression, the whole idea of having, being against randomization, whether it is in the experimental design or in sampling, or in the form of permutation tests in statistical inference, all those randomized tests that try to be non-parametric, or even in Neyman Pearson test construction, when you randomize the, you create randomized tests to achieve a fixed, say, level. The real idea being against them is that these classical models, these classical fields, actually, well, by field, I mean the whole classical experimental design, the whole classical sampling theory, they are usually based on the idea of unbiasedness. You know, all these different designs, they try to, two main stories. Where first, they come up with an arrangement of the data that gives a smaller variance of what? Of usually the mean, estimated mean, which they try to make it unbiased. You know, so a sampling strategy, which is a design plus a selection of estimators, the sampling design and the selection of estimator is mostly in classical sampling is around creating unbiased estimators. Most of the estimators, when they studied them, okay, are they unbiased? And what kind of weighting we have to use in order to assure unbiasedness? And then, okay, if I stratify, do I decrease the variance of that estimator. The same story holds true for designer of experiments. In the design, most classical design, block design, and Latin square design, Greco-Latin, whatever designs that you guys know of, they are first the same story. Try to reduce the variance. Some of them, they try to reduce the burden of adding several treatments at the same time, like factorial designs, and assure that the estimates are unbiased. And one more important thing, within these whole domains, the p-value is central. Your randomization gives you a p-value, man-made randomization, that you introduce a distribution to your observation, especially in finite, specifically when the population is finite and the number is known, the size of population is known, you create, you have to use, or not you have to use, it has become customarily to use p-values. So, p-values either coming from the a superpopulation model versions of it for the sampling, p-values, or it's coming from some sort of randomization that you get p-values from. And Bayesians, from get-go, it was a paper by, I forgot, a paper by Bickel and Blackwell way back then, that they showed that unbiasedness cannot be combined with the idea of Bayesness. So either an estimator is Bayes or it is unbiased, or it is biased. So unbiased Bayes are really, it means that you know the estimand, you know what to estimate. So you don't need to collect data anymore if you require both of those. And also p-values, it has been shown, Lindsley paradox and so many other similar things, that the posterior probability of a hypothesis given the data in the Bayesian domain can be quite different from the p-values that people use. So it has been written by so many authors in the Bayesian domains that to show how bad the p-values are, and especially p-values, the theory of p-values, which is not really totally a frequentist theory. It's based on, it is totally based on, it's a semi-frequentist idea. It is based on the data, unobserved data, pre-experimentally, some pre-experimental against likelihood principle idea, and somehow depends on the observed data. You are trying to find probability that your statistic chosen is under all possible values are more deviant from the observed value had the hypothesis been true. Under the hypothesis given, you calculate probability of a statistic given the observed value of the statistic. A statistic being bigger, some notion of bigness, or being more distant from the observed value of it. So somehow this goes against, it goes against likelihood principle, which is the backbone of the Bayesian ideas. So p-value is against Bayesian paradigm. Unbiasedness does not fit within the Bayesian paradigm. So what we should do? anything that is related or based upon these two ideas should be less valid. The great Dave Basu, I was a student then, and he was coming to Iowa State way back then in 70s. And Oscar Kempthorne, a big proponent of the Neyman-Pearson randomization, Fisher randomization ideas. They had a big discussion again, going for a whole summer, and later continued by them. And a lot of papers Basu published. He tried, and Kempthorne was trying to defend. He was trying to show that how sampling design, randomized designs are not optimal. Based on those ideas, obviously, people are not only politicians, they are scientists, statisticians, and they wanted to, if these are true, why not come up with new ideas of generating new designs based on the Bayesian ideas? Based on, and then, Bayesian ideas is rather big story. We say Bayesian, but Bayesian is by itself is a whole class of different things. The classical version are based on the Wald decision theory, which is combining priors plus another notional loss. So Zaks and his students, they develop a lot of optimal designs, which are not randomized within sampling. And the same also, people have done similar thing within clinical trials and experimental designs, come up with designs that minimizes some optimality criteria. And there are several things, but I just want to give you the idea that it is very natural for a Bayesian to show that the sampling design is not classical sampling design based on randomization is irrelevant, because the whole idea of that framework, that mentality is based on based on all this unbiasedness and randomization. To show that this stuff are not working, obviously, they are not working. They have Bayesians and non-Bayesian. They have, instead of randomization theory, they came up with superpopulation models where they assume that a population of 300 million, we are measuring their height. That population of 800 million, 3 billion, is a set of random variables. Actually, that population is a realization of a superpopulation. So they came up with the idea of using classical statistical inference models, which is based on I have a sample space, I have a parameter space, I have a family of distributions. This family, which really, that statistical inference, this family tries to model two sort of ignorance. Ignorance due to probability. I don't know. When I flip a coin, I don't know what's going to turn out. That's ignorance. This is modeled by probability model. Statistical models, they don't know if this, they don't know this probability model. So they add an extra layer of ignorance. They use the same paradigm to construct a model-based sampling approach, so that I have a whole Y1 up to Y being capital Y, up to YN and capital N. This is the 800 million dimensional variate has a distribution. Obviously, specifying such a model is difficult. So some assumptions, okay, the simplest, all of them being independent. The response that they will collect from Siamak is different from the response that we collect from Bilal, or the response we collect from Khalil. Based on that, they have developed a whole set of model-based inferences that even though still data are collected somehow randomly or ad hoc, but in the same way that people in observational studies, they model, they put a statistical model on the data. And when you choose, when you have a statistical model, then the idea of sampling and this model, how to combine these two information becomes, even within a superpopulation model, becomes a little bit controversial and paradoxical. However, design-based models is really, they look very objective, but at the same time, the choice of the model, in addition of, if you have been working on statistical places that perform this data collection, survey samplings, there are several constraints. On top of the constraints, there is somewhere deep that it is the will or the knowledge or all the subjective elements in the involved in choosing the design that comes into the picture. So even the design-based fixed population models, there is at a higher level, there is some sort of subjective knowledge involved. Why I'm putting this in? Because later when I'm giving you a new Bayesian paradigm, I am going to use this higher level of subjectivity involved that usually the Bayesian model developed by Erickson mostly in 1962, on the 60s. That paradigm ignores, this is what I think is the problem, the cause of having these two being sort of, I think, because they ignore that extra piece, the subjectivity involved in even in design of experiment. At a higher stage, if you ignore that piece, then you are with you are forced to be faced with this kind of controversy, to having design being not compatible with the Bayesian ideas. Anyway, but before I continue that, I'd like to give you more information about what I mean by higher design. Usually, the guys on sampling design, they start with a sampling frame. Sampling frame is either a computer file or is a piece of paper with list of patient subjects on it. And I tell you, what by sampling design and all these discussions are about population where N, big N is known. All the subjects can be identified. They have labels. Whether label is informative or non-informative is another question. But we have a list. It's not like a bunch of fish. The fish, like not bunch, the fish in a lake. Okay, this is a finite population. We don't have a list. We cannot apply any sampling, these classical sampling designs, how to collect. Obviously, there are sampling designs that are based on some sort of area sampling. Anyway, before I continue, I want to just talk a little bit about the frames that can be used. I have worked with data from hospitals. Subjects come to hospitals on the Mondays a lot more than on Fridays or toward the end of the week. So, but as they come to the hospital, a sampling frame being constructed. When a sampling frame is constructed, assume I have a big computer file now. It has some order. Regardless, if you are going to retrieve the file from computer, you have to see it in some order. Usually, that order, the data are in the file, might be totally uninformative or informative. So, and so even the labels might be informative. So here there are so many other aspects of the file that I don't want to talk about. I don't care about for now. But at least if I have a file, a sampling frame, imagine that sampling frame has a list, the order where the patients or the subjects or the units are listed in that frame might be informative. The guys who are on top are the top in the class. The guys who are on the bottom of the list are those who failed. So it might be ordered list. Or it might be totally, the frame might be, the order might not be relevant on the information. And the same with, usually this case 3 is the case that people list. They use the location of the each Y value in the list. So just one column in the list matters. That column, if you keep their order, it can be a sampling frame. Or if you ignore the order and the label, you might have this simple set. By set, I mean they keep even the values are distinct, keep the distinct values for different units. So this is not in the traditional sense of a set that you delete extra, repeats. Anyway, this sampling frame, the way it is produced is very important, but usually in the classical Erickson Bayesian framework is ignored. I have a set, order in the sample is usually, by order in the sample, they mean the order in which the data being one by one selected. So I select number 1, then I go in some sort of successive one by one selection rather than a whole selection of subjects. If it is done one by one in a consecutive ways, successively, that order in the sampling, in the sample is recorded. But so there are two notions of order. Order in selection of the sample, order in the sampling frame. In Erickson model, we have order in the sampling, and either this way, but the locations are ordered in sampling, and or either order in the sampling is ignored and sample is just looked as a set of data. Okay, if these are the labels, or when we say a design, we mean the all possible a sample of size fixed n, effective size n. Okay, we mean a sample S is the collection of all possible samples of this size that has been collected based on a sampling design, which, as you see, does not depend on the Y's on the sample or outside the sample. Okay, the Y's in the sample and the Y's outside the sample. By the way, Rubin, the guy who was created this propensity analysis and all of that, has an interpretation for sampling. Sampling is two pieces. One piece is the observed, and the other piece that is not observed are treated as missing values. And all the stories about missing values, how to impute for missing values, and how to all imputation techniques, they can be recasted in a language for constructing population estimates when you have a superpopulation model. So another framework for superpopulation model is based on the notion of treating unseen as missing values and bringing all the ideas from that domain. Okay, and just a simple example. I have a population of 4. My interest is total. These are the possible samples without replacement. And this gives you the design. Simple example. In this, those frames that I talked about, the 4 kind of frames, classical statistic sampling has had those in mind. When people talk about systematic sampling, the idea was that there is information how the data were listed in the file. So let's go through the whole file with random start or random lengths or whatever. Or when you do a stratification, you do proportional to size some extra X. So you care about the extra information in the frame. But for example, systematic sampling, the idea of systematic sampling, I haven't seen an equivalent version in the Bayesian framework. For the classical sampling, the data is the pair of labels and the observed data for that label and the way they are ordered in the sample. The unordered ones are these. The parameter space is all, this has to be cap n. When you have a superpopulation model, or even a fixed model, the parameter space is all the possible values of the population vector. And the data is all the possible collections of this against for all when Y is ordered or when Y is not ordered population parameters. Now, let me go back again to this. Why we are trying to define this? Because my aim to this talk here is to give you, present to you this irrelevancy, which comes from its incompatibility with likelihood principle, and then come up with an alternative Bayesian solution. So, see, I try to get the fixed sample, something called the data. If you remember, we have a data and a parameter and sample space and parameter space. So what is parameter space in the sampling? It's this vector of length n, the cap n. What is the sample space? All the data like this, which are compatible with the Y's. For each Y, the data depends on Y. So this sample space is just like uniform between 0 theta and minus theta plus 1. X's and thetas, they depend on the observed X. So the sample space here also depends on Y, whether it's ordered or unordered. But before I go to the other stuff. I just wanted to share a simple. Sorry for I know a lot of you are very esteemed statisticians, but just to share some idea. If I have a model, statistical model, I can arrange it in this simple table. The table is columns are the data, possible data values, x's, y's, and these are the parameters, the usual binomial model. I have a whole bunch of numbers here. The rows are called probability PDFs, or probability densities, or probability mass functions. So this is one for given P, for given P being 2, this one. Columns are our likelihood. So whenever we talk about likelihood and probability density, just remember we talk about columns and rows of a table like this. A probability model is nothing but this one. When I fix data, I get the likelihood. When I fix the parameter, I get the density or PDF. Okay, and you know that the Bayesian, what they do, they put a weight over these values. Bring some knowledge to the second level of ignorance that was based on lack of knowledge about which model is the real model. Now, we want to use this idea of likelihood and density PDFs on the sampling, fixed sampling designs. Given a fixed population, a data is called consistent with this fixed population if this observed samples in the observed sample values are some coordinates of this population. So densities or probability mass functions for a given Y are probabilities coming from our sampling design that generate the data that are consistent with the given Y. So that gives us the man-made probability with the probability for a given Y. So it has a parameter, it has a data, and this is a flat probability mass function over all possible data. And this S defines this D. Likelihood function now is the same, however, looking it from different ways. Let's collect all the Y's for which a given data point, look at that column, a given data point, collect all the Y's where this given data point is consistent with all of them. That is a collection of superpopulations where the coordinate been selected have the known values in D. If we collect all of this, likelihood function based on this is nothing but this one. And if you look at it, it's obviously a flat likelihood over all these Y's. This smaller set than the omega, the whole Rn, this set has a flat density over that, flat probability function over all those possible Y values. Now, likelihood principle, which is the gold standard of being a Bayesian, you have to follow the likelihood principle, says that two problems with proportional likelihood, they have to have the same, they have to generate the same inference. So in other words, all the information in the data are summarized in the likelihood. Now here, if I have one design giving me with probabilities P1 and the other design giving me probabilities P2, remember, and both of them giving the same sample. So I have 1, 2, 4. 1, 2, 4 has been obtained through 2 different designs. And corresponding to those, I have data and all the Y's that are consistent with that observed D, which is common between these 2 designs. All designs that yield the same data, they will generate the same likelihood. I mean, proportional likelihood. The likelihood coming, remember, consistent data are the same, regardless, is independent of the design. Consistency is independent of the design. I have fixed the Y, whether it's ordered or unordered. And the likelihoods are going to be what, my friend? The likelihoods are proportional, meaning the designs are the same. Eric, meaning that the inferences coming from the different designs are the same, should be the same if the likelihood principle is accepted. And remember, likelihood principle, Greenbaum, it's a famous paper and it's still controversial, showed that if a statistician believes in sufficiency, and if a statistician believes in conditionality principles, sufficiency means all the information, you can base your inference on sufficient statistics. Conditionality says that if I have ancillary statistics and I see the observed value of it, the inference should be based on the sample space restricted by the ancillary, observed ancillary. That inference is the same. So the these two are usually done by practice. People, you fix your sample size. Sample size is an ancillary statistic. Is not usually assumed it's a random phenomenon, even though it might be random, you deciding on the sample size. But assumed to be ancillary, so we run our analysis based on the given sample size. This is conditionality. And when you are writing our models and we try to, for example, in this game, we ignore in fixed population size studies. We ignore about order, because unordered samples are sufficient for this for the population. So what happens? Sufficiency is accepted usually and practiced in our life. Ancillarity or conditionality principle is practice in our life. If you accept these two, you have to accept conditionality. And if you accept conditionality, you have to accept that designs are, if you accept the likelihood principle, then you have to accept that designs are irrelevant within that framework, within this framework. And when with the same structure that I described, you can define a Bayesian paradigm that Erickson did. And based on that, based on this Erickson design, Erickson formulation of the Bayesian sampling, the posterior is proportional to the design and the PY and the prior that you put on Y's. And obviously, if you look, just get the proportionality, becomes irrelevant. The posterior, making inferences about the whole population vector, depends only on the data, and the design is irrelevant. It's coming from the previous story. So this is very strange. It tells you, forget about design. And everybody talks and knows that design might have some benefit. Regardless of how we are formulating the story, design is relevant. And for this reason, even though these results were proved way back then, still in 2023, 24, still people are using sampling design. Fixed. Why? Because there are some useful stories behind them. And an attempt to construct a Bayesian framework where we can merge and get a marriage of the two ideas into a single story, that would be beautiful. So what I really did here, we did, actually, me and Glenn Meaden from University of Minnesota, Glenn and Malai Ghosh, they have done a lot of Bayesian sampling. They have a monograph on Bayesian sampling. So it's one of his interests. No, he has retired, but is still active. Anyway, we came up with I just jump over this stuff. Imagine. I just want to describe this new way of looking at it. If you want to read more about this new formulation of Bayesian thing, there are two papers. One of them, by the way, is published in Pakistan Journal of Statistics by Glenn, and the other one was published by in Sankhya in 2010. You can read the details and some practical examples and stuff. But the idea, just I want to share you a new way of looking at this. Remember I talked about the frames at the beginning, and frames have information, systematic designs. So for us, we change the parameter space from this parameter, this omega d, to this one. I have the frame, but the observed frame, the order in which they have been appeared, is one of the possible orders. And given an order of the frame, so there are in factorial orders that you can have your frame, the computer construction. Remember, by the way, before I continue, I give you a simple example to see the idea. If I want to generate a sample, a small random number, see what I do. I want to select something random. I have an urn, I put some marble in it, and I shake the urn, and then I pick it up. While I'm shaking the urn, what I'm doing, I am putting a prior on the order of the units in the population. This piece is not modeled within the Erickson formulation of the Bayesian sampling. So what we said, he said, okay, we have a permutation in which the sampling frame was constructed. An order. The observed sampling frame is one of the possible orders. So there are big N factorial possibles. But over this, all this permutation space, I can put a prior. Then given the prior, we can have a Erickson part, which is a prior over the observed n-dimensional y. N-dimensional y. This would be our new prior. This given, now imagine here, you can do it by simple calculations, that if I restrict, if I do, say, for example, if the prior over pi, those in factorial, is uniform, I don't care about any of them. What I'm doing, I'm just shaking my urn, right? I'm shuffling, because I hope that I am creating equal, giving them equal number of chances, any card to pop up. If you apply a uniform prior over all of them, you can get both SRS without, as a marginal of this prior, when it's restricted to observed data, or you stop at some point. You start generating, and because this is what you can specify over all the L1 up to label 1 up to L cap N. So it can be implemented in a successive ways, just following the conditional factorization of probabilities. You can that the piece observed is this piece. The remaining piece is this piece. The prior can be decomposed as this piece. Actually, for simplification, we can add this. More generally, this is the case, but we can decompose it this way, times observed, unobserved, given the observed permutations, the initial segment that we saw, and the observed values of them. And this way, we can restrict our sample space after we have seen these pieces. We have a new omega, which is based on pi. I mean, sets of consistent values, as we saw in the general framework. And based on that, we can construct posterior over the unobserved permutations and their values given sample and observed stuff. The simple compute is with the available computer and automatic facilities, we can do all of this stuff for sure, right? And then we use this framework. We showed that the estimators of total that are being generated are stepwise Bayes, and stepwise Bayes means there are unique Bayes with this new prior. There are then there is not unique Bayes. If there is unique Bayes, we know the estimators are the estimators of total are admissible. But if it is not, then we restrict the class of Bayes estimators, and we try with a new prior to find a Bayes within that class, and we continue this up to we get unique at the end of this hierarchy steps. We get a Bayes estimator. That's called a stepwise Bayes, and that is admissible estimator. Anyway, that was. Thank you for paying attention to, and it's really over time. Sorry for being speaking over time and not being so precise as it should be, but I tried my best. Thank you. As in Farsi we say, به پایان آمد این دفتر، حکایت همچنان باقی. It's the story, the notebook is finished, but the story is not told, still unfinished. Thank you.
Well, thank you, Professor Noorbaloochi. And now it's the time for Q&A. See, I'm not an expert on this, so I'm an energy guy, but we do use statistics and modeling for various aspects in, let's say, for like predictability of weather, for solar generation, etc. So my questions I'll put it in the end, but I'll encourage somebody from the audience, if you want to pose any question for Professor Noorbaloochi, please do so. Professor Jali, can you go ahead?
Hello, do you hear me?
Sure.
Do you hear
Yes,
me?
yes. Yeah, I can hear you.
Thank you very much, Siamak, for your nice talk.
Thank
and very informative one. And I hope that the people from the audience can have may have some questions for you. We are waiting for them to ask the questions.
Thank you. There's something in chat. Maybe I can read the chat. Moving. Oh. Did you guys didn't see the slides moving or what?
Yes.
Oh. Because I know I saw a note says we don't see the slides moving. I hope.
So meanwhile, if there's any question from the audience. Professor Noorbaloochi, so how do you see the use of supercomputing or artificial intelligence, because those the most emerging aspects of predictability, or even trying to figure it out, the advanced predictive analysis that we see that with the artificial intelligence and supercomputing, the capability to model something where you can have pretty close to extremely good precision and predictability. Over the course of your career, how do you see the statistics, or in general, or in your field, but particular space that you worked, how this advanced computing has influenced your field of work?
I tell you, this is very, 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 very good question. Very good question. I tell you what, it's just not I'm trying to butter you up. No. I have heard this question from several people. Statistics has been increased to such a big domain that the classical framework for presenting statistics are no good anymore. Still, stories of clinical trial, sampling, statistical inference, taking a sample and making an inference, they are highly relevant. But with the advancement of data collection using computers, we are faced with a huge set of data. Huge by mean not only a lot, but highly big dimensions, high dimensions, super high dimension, that they require a lot more human to work on it. Not statisticians only. Who is a statistician? Somebody who works with the data. So nowadays, at any university in the world, almost at any department, there is somebody calls himself electrical engineer who does a statistic, but a statistic that he generates is not my statistic. He generates GBM. He generates random forest. I mean, this is 1982. He generates all cool models for dynamic updating and constructing, producing the predictors that are needed in moments. If you run a Tesla, you need predictions not only done precise, done fast, quick. And these are questions, challenges that people who work with data, they may not call themselves statisticians, and they should not. They are working with the new domain of data. And really, one thing in order to maybe organize it or get more benefit of this huge interdisciplinary science, the word science, empirical science, which simply we say science, depends on data. And it's not science now is past science. It is more business, and business is great. Tesla uses all the science to make a car that goes without, say, with less errors due to human agent in the system. Or what I thought about this, I think the one best way of organizing this new involvement of scientists with data, which artificial intelligence is one piece. You tell me, econometrics, psychometrics, all the engineering, anywhere that the data is available, right? Is to use the medical school's paradigm. within colleges. Look, in the medical school, we have several fields. Surgery is an independent department. We have internal medicine independent. All of them huge, so many, but it's called medical school. All of them have their own specialties. People work there, think there, type, generate science, provide service. A statistic has to be the same. This idea of restricting to the 140 credit or 120 credits that is common all over the world, coming from American educational system. It's good. It by itself, 140 or 130 restricts the topics to be covered within 4 years, within 10 years, 8 years, whatever, after your PhD. You are forced to learn a stochastic process in this special subdomain. And it's okay. That's why we have so many more humans. Other people can, instead of working on stochastic process, on the Brownian motion, they can go and work on time series, dynamic Bayesian models. You know, artificial intelligence. What? Artificial intelligence name. It's so many, even neural network has, I don't know, at least I didn't work on it, but I used some of the neural network. But there are maybe 4, 6 different subfields in neural networks. So people working to use this big, whether we like it or not. I think if we can come up with a new paradigm of defining a data science, a school of data, or a school of, instead of medical school, a school of statistics, have all these groups working on the ideas related to generate inferences of different types. For example, one big story. There is actually an institute in America for it. Patient-centered medicine. Siamak is sick. You can measure Siamak blood pressure, the cholesterol level, and 500. So Siamak becomes a vector of length 500. Each coordinate is a test or an indication or something, information about something. Can I use all this high-dimensional data? Yeah, one. It's not a time series. Time series are high dimensional, usually repeated the same thing over time, or in a spatial statistic, the same thing is over 2-dimensional space. But I have a variety of measurement on the same subject. Can I make inferences about his heart attack? This single person. This, not one person. It needs a school to study this kind of questions. And not now, for long time, come up and continue the same thing. So I think a better paradigm would be to, and have them in one school is just to facilitate them to talk to each other and benefit from each other. It's otherwise, whether we want it or not, almost any university in the United States, even in the Department of Literature, they use some sort of data. They use some sort of data to and some way of generating information. The text mining, which is very common, right, in Google. Google Research Institute in New York and in California. What they do, they are doing the Bayesian, classic, sampling, market. It's just any statistical available. If the guy who is working there knows, they will use. So human barrier is also very important, remember, regardless. And the more important, second story, they develop models that no university develops. I mean, now the boundary between universities, departments, between universities, university and research institutes is gone. People and everybody is good people. Remember, it's not about. I remember when I was younger, way back. Because of our culture, I hated, not hated, sort of. I disregard people who are in business. I disregard people who are, oh, these are not RF. They are not Sufi. They are looking for money. Come on, money is a simple thing. For example, look at the Tesla guy. You know how much he's happy that generates something new. Now other companies do. I mean, for me that don't have money, maybe his money is big deal. But for somebody who has money, it is the ideas that makes him happy to live, talk, generate, use his money. So I'm just giving my loose ideas and sharing them with little precision. That's it. Thank you.
No, you put it very well, and I see the gestures or with such a passion that you responded my question. I see that how recent advancement in computing have advanced or magnified the level of work that is required. Thanks again. So we have one question in the chat box by Mr. Babak Chaudhary Uski. Sorry if I pronounce it.
Babak.
Yeah, Babak Chaudhary.
Yes.
So he says, thank you, Dr. Noorbaloochi, for the interesting talk. I work on clinical trials design, particularly on the design of adaptive trials. Mm-hmm. My question is about the application of this framework to trial design, specifically in the phase 3, phase 3 or confirmatory settings. Yes. How can we deal with the strong control of overall probability of false positives? I'm talking about the control of the type 1 error rate when choosing Bayesian design, and it being dependent on the choice of prior distributions.
You are asking a tough question, and I don't know the answer. But generally, the adaptive designs in clinical trials, I just give you my general ideas of adaptive designs. Adaptive designs are sequential designs developed originally by Abraham Ward. But recently, they have become very popular in clinical trial because it gives the freedom to modify the design at the stages of its development. If patients show adverse events, you have to modify their designs. But by changing them, it requires new ways of analysis of those. So it's not only the design that is like you randomize at several stages, depending on the outcome observed in the prior stages. The methods to analyze that is what is out of hand. Even there are methods like people in causal inference. They have came up with what? Smart design, SMART, which are sort of adaptive designs. But it's beautiful name, so it can become popular. So they have to calculate how to analyze those data. It requires some sort of sequential propensity calculations or some sort of dynamic inverse probability weighting, and getting those weights that really or essential in the adaptive designs to create good estimates. And forget about testing. Testing is, testing requires a good, if you are going to get some sort of probability, even in the Bayesian, you have to have a good model. And you can run some model, as we do. We always do something. But when you are trying to, if you want to sell it to the journals, to get it published and people say, ha, he did it. you have to come up with a good IPW weights to get the good estimates. And those IPW weights, which are very these days common in adaptive designs, are study design based. But study design, what I mean, when you start a study or a clinical trial, you say, okay, on top of this outcome and this intervention and this design, we are going to collect this set of covariates for each subject, because we know that we will have non-response, we will have people who will not participate and all that stuff. Anyway, these covariates, and we are going to use these methods, regression, mixed model, tell me what, repeated measure, GEE, well, so many garbages. And they have their Bayesian versions. They have robust versions. Look, deciding on this whole set of garbages, methods, covariates, these, how to collect them, how to implement them, these are like a study design garbage. That IPW depends on this. So that's why most of the time, I mean, you have seen one time they tell you caffeine is good for you, drink coffee every morning. The other day say, oh, it's really bad. One day they say wine is good, the other day say wine is horrible. Because, and both of them are right, good people, not anybody cheating. The covariates, the statistician that choose the model, all of them are involved. Science is not as objective as we look. When I was younger, especially when I see a journal of New England Journal of Medicine, JAMA, Journal of American Medical Association, Lancet. These are like famous names in my field. When I saw those stuff, oh God, this is good. When I look at JASA, a paper in statistics. Look, right now, when I was a student reading Erickson papers, it was oh God, this is good. Now over time, I noticed that these are something people said. They use formulas. It's nothing important, nothing respectful. Read a paper and throw it in the garbage can. Somebody talked something and used the pencil and wrote it and typed it and put some formulas, big F and small G and cap. No, the real thing is, you see, there is a high school kid have come to the university, graduated, a young man, human like me and you, who is trying to generate share his ideas, and he has learned no ways but using those methods. If the outcome is a Tesla that can drive in the street without the driver, that is the output. If the outcome is make people in, remember, I remember Oscar Kempthorne was talking about something big. Oscar Kempthorne was experimentalist. They're running a lot of experimental design. His book is famous. He was a student of Fisher himself. He said he was ranking Fisher higher than Einstein. And the reason he had, this was his. He said, in genetics and running the statistical experimentation in crops, he came up with methods that solved the problem of famine. Way back then, the world was faced with lack of crops, wheat. And this design of experiment, producing new crops that require less land, less water, less diseases, so many impacts of statistical experimentation, right? Generated a safer world. If this can be done, forget about the papers, and they are there. Good, we use them. We have to learn them. We have to spend time, teach them, but we have to teach the student. I remember something. It's just very international meeting. I want to say this. way back then, when I was giving a paper to my students to read, if it has a name, Ahmad, Reza, they would read it with less respect. They will, I would see it. Why? They would criticize a lot more. They scrutinize. But if the name was Filippo or whatever, I don't know, some European name, the number of criticizing, the amount of criticism would decrease a lot. As if now it's the word of God. Destroy that. Don't believe in anything. Just read yourself, read, understand, and look toward the end, how good you are going to be to your community, your either it's science, it's that's the real story. The rest is my language, garbage. Sorry.
Thank you, Professor Noorbaloochi, for such a passionate talk, and you know, the last comments that you made, that it's not important that what you're going to do with those models, but it's just what good or meaningful can you bring out of these models in serving the humanity and making anything that's applicable. So we are grateful, and so I think we don't have any further questions, so I'll conclude right now.
Thank you.
And we are so grateful that you took your valuable time and joined us in this effort. This is, as I said, that we are driven by the ECO Science Foundation and the UISMS, Professor Rijali, his leadership and mentorship. So we would continue to do our job in terms of promoting maths and science in the ECO member countries. And we greatly value the efforts and the hard work that the professionals like yourself, and we will continue to engage with you in similar topics, perhaps on more broader perspective of statistics in terms of that's more relevant for the general audience. Perhaps we look forward to having a similar session again. Thanks a lot. Thank you all the participants.
Thank you, and hope to participate in these meetings more. Thank you very much.
Yes, we'll keep you bugging and inviting you in for other, or so we have this every day, every month we host one lecture by so thanks a lot, everybody, and see you next time.
Thank you.
Bye-bye.
Thank you, guys.